Good afternoon, and welcome to the Amazon Aurora Deep Dive session. My name is K.D. Singh. I'm a solutions architect with AWS Consulting Partners team, and this is my colleague Scott Watt, who is a solution architect with AWS Technical Partners team. We like to keep some time towards the end of this session for Q&A, and we have a lot to cover, so let's get started. So Aurora is MySQL compatible, enterprise-grade database service designed for the cloud. In many ways, it's a game changer when it comes to traditional database systems, which don't really scale that well and don't perform that well and are costly. There are many technical enhancements that we have done with Aurora to make it perform really well and scale really well, and still the pricing is how we typically price AWS services: pay as you go, no lock-in, and no upfront commitments. We'll be spending a bulk of this session on how we did things. So in this particular slide, I'm going to spend some time covering some of the key features that we have with Aurora. Amazon Aurora is designed to be very durable. The data volumes in Aurora are actually divided into segments. Each segment is 10 gigabyte each, and each segment is 6-way replicated across 3 availability zones. So that's a lot of durability. It's designed to be fault tolerant. All these data segments across availability zones make them fault isolated, and also it can withstand loss of 2 out of those 6 segments without affecting your write availability, and it can withstand loss of 3 out of those 6 segments without any loss for read availability of your database. So it's really fault tolerant. It does continuous incremental backup of your data in S3, in Amazon S3. S3, as most of us know, is designed for 11 nines of durability. So this continuous backup feature is really neat. It is very high performing. For similarly configured hardware, Aurora gives you 5 times the performance of standard MySQL. With Aurora, you can run up to 15 read replicas. These read replicas can be put in any availability zone, and with these read replicas, you can get really high read performance for your applications. But with these read replicas, you can also use them as failover target. So if something were to happen to your primary Aurora instance, any one of these read replicas can be used as failover target, so you really won't lose any availability of your data with them. It is self-healing. So it automatically detects any issues with its nodes and disks that it's running on. It uses SSD behind the scene. It detects that, and if it finds some problem with any of the nodes or disks, it's going to replace them seamlessly without affecting availability as well. And then it uses features like survivable buffer cache. So what we did with Aurora was we took the caching layer, which is available, which is present in pretty much all commercial databases, and we took it outside the database tier itself. So even if your database has to restart for any reason, your cache would survive that. So you get instant crash recovery because of that. And finally, it's designed to be very secure. By default, Aurora is going to run in Amazon Virtual Private Cloud or VPC service, giving you network isolation and all the features that VPC offers, including subnetting and security groups, etc. You can also encrypt your data using SSL AES 256-bit keys for data in transit. And for data at rest, you can encrypt your data with Aurora as well. And those encryption keys for data at rest can be managed using the Amazon Key Management Service. So it's very seamless and works well with other Amazon services. So we launched Aurora, made it generally available in July of 2015. And since its launch, it has been widely used, and now it has become the fastest growing service in AWS history. It used to be Redshift, but now it's Aurora. So we have seen really rapid usage, and we have seen partners big and small, as well as customers big and small, use it for a ton of different use cases. whether it's for business applications and enterprise apps, or whether it's for web, social media, gaming, IoT, you name it. People are using it for all kinds of use cases. Let's look at some of these customer examples in some more detail. The first one I want to talk about is Expedia, which is an online travel portal. They actually operate more than 150 sites in 70 different countries all around the world. So they have a ton of data coming into their travel marketplace. This is data that has key business insights, and they want to run data real-time BI analytics on top of that data. Their current SQL server-based solution was deemed too expensive. They were not really happy with its performance, as well as the data volumes were increasing. The performance was not scaling well for them, and it was getting too costly for their liking. So they explored some solutions. They looked at leveraging Cassandra with Solar Index, but to get the amount of performance they needed, the memory footprint had to be huge, so the number of nodes they had to deploy for such a solution made it very costly. With Aurora, they were able to scale effortlessly to the amount of performance they wanted, and they got to do it at a much lower cost point as well. The next one is Thomas Publishing. It's actually more than a century-old business, and their goal is to somehow bridge the gap between buyers and suppliers. They started with digital publishing, but now they have a lot of different companies under that entity. And they had been actually using Oracle for their production workloads. And they were facing problems in terms of scaling their database well and getting the performance they wanted to get out of it. Another issue for them was the upfront investment. They had to make a lot of capital expenditure just to get the infrastructure, as well as Oracle licensing required for their needs. So they ended up leveraging Aurora as well. So for migration of their production database, nobody wants their production database to go down. They want minimal or no downtime. So they leveraged two services in Amazon portfolio. They use the AWS schema migration tool that helps migrate or convert things like views, stored procedures, and functions in Oracle and Microsoft SQL space to similar attributes that can be leveraged in Aurora. So schema migration tool was good for them. And then they use the AWS database migration service, or DMS, to migrate the actual production data over to AWS. The database migration tool, it's a standalone service. You spin up this service, you point it to your source database, and you point it to your destination database, and it does all the orchestration required to move the data for you. So with using these services, they were actually seamlessly able to bring their data over from Oracle production database to Aurora in less than 4 weeks. So they are one happy customer. A couple more. ISCS is in the insurance industry space, and they have been using Oracle and SQL servers for the Microsoft SQL Server for their database and warehousing needs. For them, cost was important. These solutions were getting to be very costly. We see a pattern here. We actually designed Aurora to be similar in performance to high-end commercial databases, but up to 1/10 the cost of these high-end commercial databases. So no doubt these ISCS people also like the cost they were getting with Aurora. But another problem for them was maintenance of their database. The ongoing mundane tasks that you have to do day in, day out just to keep your database up. With Aurora, that pain point went away because Aurora database engine is actually managed by Amazon Relational Database Service, or RDS. So things like provisioning your database or patching it, detecting for any issues or problems, and repairing those problems and doing backups. All those things that we can deem to be undifferentiated heavy lifting items that you just have to do to keep your database float, they are done and managed by Aurora for you. So they were really happy with migrating to Aurora, and on top of it, they actually realized 70% cost savings over their current SQL Server deployment. And the last one is Alfresco. which is an AWS partner in the enterprise document management space. And for that, it was all about scaling. So they wanted to scale to over 1 billion documents. And even at that big scale, they wanted a sub-second response time for user requests to these documents. So they actually leveraged Aurora, and they were able to scale to 1 billion documents with a throughput of 3 million documents per hour, which actually was 10 times better than the performance they were cutting in their existing setup. And they are migrating from big data centers to leverage Aurora now. So let's get a little bit into why we designed Aurora. If we think about any relational database system, at the very core of it, it's some store and some compute. And typically, this store and this compute is all running on a single box. There are different layers of functionality. If you look at the picture, we have SQL, transaction, caching, logging, and storage, different layers of functionality. You can think of these as different tiers, but the bottom line is all of this is running on a single box. It's all well and good if you're not loading it that much or if your data volumes are not increasing that much, but that's not typically the case if you're a successful enterprise or a successful user. Volumes increase. So to scale your database with it, the first approach you can take is vertical scaling, or to scale up. You have a smaller box, you just get a bigger box. That bigger box is not sufficient, you just get a bigger box than that. But as you can imagine, there are actual physical limits beyond which you can't scale vertically. You just can't get a bigger box. So people have been using, and this database is 30, 40-year-old thing, so people have been using different techniques over the years. Some of them are highlighted here. Sharding is one, which means creating horizontal partitions of your data essentially and putting them in different nodes. But the bottom line is, if you want to run SQL queries against your data, you typically want to do it against the full data set. So in case you have data distributed in different nodes, your application now has to deal with where should I send my query, which node what is sitting on. So there is a lot of complexity related to sharding that you have to manage. And if one of the node goes down for some reason, you have to deal with it. You have to deal with data loss. So there are issues with scaling it. Shared nothing approaches were also popular. In this case, your application does not have to deal with how and where to send the query. It's handled by your SQL layer. So it's a little bit simpler on the application side of things, but it's still a problem if the data node goes away. Data is lost. So as you keep on increasing the number of nodes in your database cluster, the overall availability of your database goes down. And finally, shared disk. The key idea here is that you essentially want to fuse the caches across different boxes or different nodes in your system so that they are reading off of the same caching layer. This is a little bit better in terms of data loss, etc. But the problem here is when we load the system a lot and a lot of transactions are happening, this caching layer and the caching algorithms, they can become very chatty. They just need to move a lot of data back and forth and can lead to problems like hotkeys. If you look at any of these pictures, the main thing is that you're actually replicating the same stack over and over again to scale out. So you fundamentally run into scaling issues with it. But this is how things were done in the old world. Now imagine if you had to design a database today. What would you do? You would design something that can scale out easily. If you have monolithic tiers of your application all running in a single box, that's not a good pattern to follow. You want to design something that can scale out. You want to design something that is self-healing. And you want to design something that can leverage other modern services available in cloud platforms. So you'll actually design something like Aurora. So in Aurora, this is the Aurora picture. I'll spend a minute or two on this. What we essentially did was followed the service-oriented architecture design patterns. So again, we have the same stack, SQL, transaction, caching, logging, and storage. But what we have done is we have broken them out. Logging and storage is now a separate system. It's being handled by a separate system now. It's not part of the monolithic stack anymore. And then what we have done is we have done this automatic backups to S3. If we think about traditional databases, what these databases had to do was your DB or SQL layer would write redo logs to your storage tier. But for those systems, the storage tier were just dumb blocks. They were just blobs of storage. You just put things into them. They can't do anything about it. You have to manage everything. In this case, what we have done is this storage layer is smart enough, for example, to do things like take the redo logs that SQL tier is giving to it, and then create data pages from those redo logs on its own, and store them to S3. So it has some smarts built in to take some of the load off of your DB tier and do storage-related items or logging-related items on its own. So it can obviously scale independently of your DB tier and do things on its own. So it's a big win there. What we have also done is moved caching out of your DB tier, which gives you survivable buffer caches and instant crash recovery. In this case, if the DB has to be restarted, the cache is still populated. That data is not going away anywhere, so things work better. And finally, to orchestrate this whole system, to run your database, Aurora database, there are control plane services to make the whole thing happen. For example, we leverage some of the popular AWS services like DynamoDB, which is going to contain your volume metadata. So the volume metadata is now in DynamoDB. It's outside of the main stack, so it can scale independently, and you can get really good throughput, read-write performance out of DynamoDB to get to your metadata. We are using the simple workflow service, or SWF, to do things like starting an instance or scaling an instance, so it manages the workflow for doing it. And finally, we leverage Route 53, which is the DNS service, to do failovers. Using Route 53, if the primary instance goes down, Route 53 is going to do the DNS magic to failover to your replica or to your failover instance seamlessly, and it can do it in 1 to 2 minutes. So this is how SOA principles are actuated for Aurora. Now let's look at some performance numbers because this is important. So what we did was we used the MySQL sysbench benchmarking suite, and we ran our benchmarks against it. We used 4 client machines with 1,000 connections each that were reading from this Aurora database. And we were able to achieve more than 100,000 writes per second and 500,000 reads per second using this benchmark, which are really, really good numbers. Not long ago, people were talking about 1,000 reads or writes, so this is pretty big. But as we know, benchmarking numbers done in a lab environment don't really mean much in the real world. In the real world, we have to deal with real problems. Real problems like there are, actually, let me first talk about how we got to those numbers before I get into the real world. Let's stay in the lab for a minute. If you want to do benchmarking on your own, we have provided some guidelines or a guide so that you can get to those numbers yourself. At the bottom of this slide, we'll be putting these slides online shortly after the event, or you can search for it, the Aurora benchmark guideline document, and you can get to how we set up the benchmark. You'll see we provide you information like use the same VPC for your client machines as your Aurora database instance, use the same AZ where your database instance is running. You use more advanced EC2 instances for your Aurora clients with enhanced networking turned on for good network throughput. You have to tune your Linux. We show you how to tune your Linux to get good performance. So you can get to those numbers. But the more important thing is these are some of the best practices that you can also follow to get good performance out of Aurora. Now let's go to the real world. In a real world, things are different. You have to contend with things like there are multiple users, each making multiple requests. It's not going to be a single user with a single request, and you can't measure that. You have multiple requests going on. That decreases performance. You have situations where your metadata would not really fit in the data dictionary cache. Your metadata would overflow it, leading to poorer performance. You would have to deal with your caches won't be big enough to hold the data. So buffer caches are going to overflow. And finally, in a real world, you never want your database to go down. You want fault tolerance, you want high availability, which translates to using read replicas and failing over and things like that. So since this is a enterprise-grade database solution, Aurora is, we want to test its performance against these real-world scenarios. So we did some experiments. I'm going to go over those experiments now. The first experiment was when there are contending requests, what happens? So in this case, we scaled the number of user connections. We are again using the sysbench benchmark, its OLTP workload with 250 tables. And we scaled user connections going from 50 to 5,000. And we saw that Aurora scaled with its performance actually improved. And if you look at MySQL, the second column here is about MySQL. Its performance actually degraded, and Aurora was able to perform 8 times better than MySQL in this case. And just for your reference, the MySQL that we compared it against, it's not a small instance. We were using 30,000 provisioned IOPS in a single AZ to run MySQL on RDS. This is probably the biggest box for MySQL on RDS that you can get in Amazon. So we compare it against the best we can get in Amazon environment, and Aurora still performed 8 times better in this case. The next one was about the data dictionary cache. So what we did was we scaled the table count, and we went from 10 tables to up to 10,000 tables, and we looked at the throughput. And we compared it against 3 different flavors of MySQL running in Amazon. The first one was, again, your RDS with the MySQL 30,000 provisioned IOPS. And the second one was I2 instances, which have good I/O to its local SSD instance store. So we leveraged that. And the third flavor was using RAM disk. For MySQL using I2 8 extra large instances, which are really good instance types in EC2. And again, across all these different configurations, Amazon Aurora performed up to 11 times faster. What this shows us is that I/O is not really the only problem. It's not really a problem here, because these configurations, for example, the RAM disk configuration, I/O is not what's bounding the performance for MySQL here. It's internal things like log sharding and algorithms that are happening internal to the database tier, which are causing the performance not to scale. The next experiment was, what if your data is bigger than the buffer cache? So we started with a gigabyte of data set, data volume, which would pretty much fit in most commercial caches out there. But then we scaled it up to a terabyte, and when we saw what happened, Aurora performance, it went down. It was stable till up to 100 gigabyte, and then it went down about 4x. But if we look at what happened with RDS, its performance dropped more, and it performed early. The performance, it dropped more, and it dropped earlier than when it dropped in RDS, so in Aurora. So we essentially see Aurora performing up to 67 times faster in this case, in case of scaling your data sets. And just to be sure, we ran the same experiment against Cloud Harmony TPCC benchmark, which calculates throughput numbers. And there, Aurora was performing 136 times faster. And the last one I want to talk about is running your databases in a fault-tolerant, highly available mode, which essentially boils down to running read replicas. In case of RDS, when we do read replicas, you can do up to, I believe, 5 read replicas with RDS MySQL. If you do that, we see that the replica lag goes from a few milliseconds when we are doing 1,000 updates per second to over 300 seconds when we scale your updates to 10,000. So that's a lot of lag in replicas, which means that if you were to fail over to a replica, you will lose a ton of data. And if we look at Aurora, as we scale from 1,000 updates to 10,000, the lag, replica lag is fairly constant. It's not increasing much, and it's 5 milliseconds. So that's really a good lag number to have for failovers. So in this case, Aurora was performing 500 times better than similarly powered MySQL instances. So how do we do that? If you want to scale your database performance, there are some things that pretty much any commercial database would do. Things like log sharding or improving algorithms on the database tier. But you need to do more than that. It's not really architecture work at that point. You have to do things like you either have to do less work or you have to do work more efficiently. So it's to scale your performance, it's all about IOs. You can't afford to do too many IOs. So how you do IOs and how many IOs you do matters a lot. And then how many network packets you're driving. When you're talking about network attached storage in a distributed system manner, if you don't have monolithic blocks, you have network attached storage, then the packets per second to your storage matter a lot. You don't want this to be a high number. And now, you can do 1 million to 2 million packets per second from high-end hardware like EC2 with advanced networking, but still it's a constrained number. Beyond a certain point, it won't scale, so you really can't afford to do too many network packets. And then you can't really afford to have context switches. If you have a lot of context switches, the performance is going to go down. So a lot of architecture work we did to make Aurora perform better was in terms of reducing the number of IOs, reducing the number of packets per second that we are driving to storage, and moving towards more asynchronous processing. Now, to open the hood and show you how Aurora does these things, I'm going to have Scott tell us about that.
Thanks, Katie. All right, so let's go ahead and take a deeper dive into some of the architectural components that go along with Aurora and even kind of help speak to how we achieve some of these numbers that Katie just presented. So to start with, this is a simple representation. This we consider an Aurora cluster. So it's got at least one primary database instance. It has a storage tier that covers 3 availability zones in whatever AWS region you're running in. And there's 6 storage nodes within that storage layer across those 3 availability zones with 2 storage nodes at each availability zone. And that cluster backs up all of its data to Amazon S3, so getting the durability and the availability that comes with S3. This is a deeper representation of a cluster, so you've now got read replicas. So we have, once again, our primary instance leveraging the storage node. We now also have our read replicas. And because that storage layer covers 3 availability zones within AWS region, I can place my read replicas in any availability zone within that region that I want to, whether it be as the same as the master, or it could be different availability zones from that master. And on top of that, these read replicas are actually your target from a failover perspective. So when there is a failover with the master, those read replicas are going to be promoted to the master. So having the ability to place those in availability zones that are different from the master to help guard against any network connectivity issues with the actual availability zone or issues with the master is a benefit to be able to use those other availability zones when it comes to an Aurora cluster. So Katie was talking about how I/O is such a big deal when it comes to databases and the performance of databases. So here in this slide is a representation of what a MySQL database running on Amazon RDS would look like with a standby database. You've got your primary instance in one availability zone, and you've got your standby instance in another availability zone. And when you do a write operation to that primary instance, what it's going to do is it's going to take and then write the data against the attached Amazon Elastic Block Store. The EBS service will automatically mirror that data to another EBS volume to deal with the durability and availability that EBS gives you. And then that same write operation is going to be issued to the standby database. And that standby database will once again write the data to the EBS volume that's attached to it, and EBS will do the mirroring of that data. But it's not just the actual data write. There's also a lot of different log files that are involved with MySQL that need to be moved around to the different storage layers, and as well to the standby instance and down to the storage layers of the standby instance. So at the end of the day, you have a lot of moving parts when it comes to the movement of data and the I/O operations that have to happen to have a complete success message and to have everything in sync between your primary and your standby database. And if you start thinking about things like network jitter or latency that may play into the equation, you now have a situation where those types of issues can impact your database and its standby being in a state where you feel comfortable, or where things are at a state where you feel that you can recover successfully. One of the things that we did with this configuration is we did another performance test. We used the sysbench write workload with a 100 gig data file. We ran it for 30 minutes against a MySQL database running in the single availability zone configuration on RDS. We ran that for 30 minutes, and at the end of the time, we found that we were able to get 780,000 write transactions out of that test, which is pretty good. It works out to about 7.4 million read-write operations per million transactions. This is excluding anything having to do with the standby database in this, because everything that you're seeing, how that standby database happens, is really part of the RDS service, and it's not really necessarily relevant to what's actually happening on the actual primary database instance as far as this test is concerned. So on Aurora, the architecture is a little bit different. We minimize and work to minimize the amount of I/O traffic that's actually happening within the Aurora database. One of the primary things that we do is that storage layer that's spanning the multiple availability zones, all the primary instance is doing is sending redo log files to that storage node. It's collecting them up, it's boxcarring them, it's combining them together and sending them in regular chunks to that storage node. These redo log files are very small, and us batching them up helps to really reduce the amount of network I/O that we're actually sending across the wire to this storage layer. And when those log files actually get to the storage layer, we end up doing 6 times more writes than you would see in MySQL, because we're writing it to all 6 nodes. But it actually ends up being about 9 times less network traffic compared with what you would see on the MySQL configuration and it having to write to its database storage system, because all we're doing is we're sending these small redo log files to the storage node. So it allows the Aurora cluster to be a lot more tolerant of what's going on from a networking standpoint, because it's sending little amounts of data to start with, so any little hiccups are less impactful to what's happening from the Aurora cluster standpoint. So we went and ran that same sysbench test against an Aurora cluster. Once again, 30 minutes and a 100 gigabyte data set. And the results of that is that we were actually able to write 27 million transactions over that 30-minute time frame, which is 35 times more than we were able to actually do on the MySQL test. That worked out to about 950,000 I/O operations per million transactions. Now that has 6 times amplification, so it's covering all 6 of the storage nodes. If you broke that down, it's about 158,000 read-write operations per storage node. So that's just a little over 7.5 times less than what it took from a MySQL standpoint. So with the Aurora and the way it's configured and the amount of I/O that it's able to save, it's able to do more, because in the background it's doing a lot less from an I/O standpoint. So let's go one step further and let's actually take a peek inside that storage node as far as what's going on. So the first step, as we already talked about, is that that primary instance is going to send its log records to that storage node. The storage node is going to put that into an in-memory queue, and then it's going to pull off of that queue, and it's actually going to persist that data and write it to disk. At that point, the data is durable on the storage node, and it will acknowledge back to the primary instance, and the interaction with the primary instance is done. That is the critical path from an Aurora standpoint. Everything else that happens after this is done asynchronously, and it can happen independent of any communication with the primary instance. So once the storage node has its log files, it's actually going to start organizing those log files and the records in those log files. And because things can show up out of sequence or not show up at all at times. And it'll find out, do I have everything? Am I missing any writes? Is there anything out of sequence? And one of the cool things it'll actually do then is that there is, for all those 6 storage nodes, there's actually a peer-to-peer gossip network that's in place that allows all of those storage nodes to talk to each other and help resolve conflicts where one of the nodes is maybe missing some data. So they'll communicate with each other and they'll say, I'm missing this, do you have this? And they'll sort all that out and they'll exchange that data so that each of the storage nodes at the end of the day has the same amount of data as all the other storage nodes, and that they resolve any missing data or conflicts with data that one storage node may have. So after that has done, and they've figured out who has what, and they've got everything in order, they go and coalesce those log records into really new data block versions, turn those into the data blocks that are needed for the database. And then periodically, once again asynchronously and very regularly, the storage nodes will actually back up that log and block data to S3. That being like, this is our durable storage place for the data that we're using in our database. Storage nodes will also go through and do garbage collection periodically, looking for old log files and data blocks that are out of date, that have been replaced by other data blocks and log files that it now has, and get rid of those. And then finally, it will actually do some scrubbing of the data. It will actually go through and read data blocks independent of a request from the database instance, and check those blocks. Verify the checksums against those blocks. Make sure that they're actually good data blocks still, that they haven't been corrupted through normal disk usage, or that they're dirty now. And if they do find a bad block, they'll actually leverage that peer-to-peer network again to talk with the other storage nodes and say, hey, I've got a bad block here. Does somebody else have a good copy of this block that they could share with me? And they'll heal themselves by sharing that data across that network again. So a couple of things about this, that input queue of the data coming into the storage node, that actually ends up being 46 times less than the data that's being transferred from a MySQL standpoint, because it's just redo log files. It's not all the other data and the big blocks that go along with writing from a MySQL database standpoint. We favor the latency-sensitive operations, getting that out of the way up front and making everything else asynchronous. The storage tier is a multi-tenant storage tier, so there are going to be patterns of high usage and low usage during the day of that, on that storage tier. So we work to take advantage of the low points in that to get a lot of these asynchronous jobs done, so that we're not putting any negative impact on the customers, but still able to get all of the work done in a decent amount of time. So one of the other things that we've done is we've kind of worked to change how commits happen in the Aurora database. So in a traditional database approach, the way that commits typically work is that somebody will do a write, and those writes are collected in a buffer. And when the buffer's full, or when their amount of time has passed, the buffer will get flushed and written to disk. The problem with that is that whoever is the first writer into that new buffer will get a latency penalty. If not enough transactions come in, or if that buffer doesn't fill up fast enough, they're stuck waiting until the actual timeout flush happens on that one, which is, it's not their fault. They didn't do anything. They just happen to be that first writer into that particular buffer. So there's a penalty on that one that's just kind of naturally exists with that approach. On the Aurora side, we've kind of changed all that one. We don't have to, we're interacting with our code. We wrote the code base. We don't necessarily have to live with the Linux file system as far as how we need to do commits and everything. So we actually, the way this works is that As soon as the first write happens, we start I/O operations. Every write gets its own I/O. It's not waiting for anything else. And then those writes are collected up in a buffer, and a background job collects those at some point. And then they're sent off to the storage node. And they're considered durable when 4 out of the 6 storage nodes acknowledge, yes, I've got the data and I've committed it to disk. So at that point, we consider it very durable. The next thing we're going to do is that we're going to look at the last log record number. In this case, it's number 47. And we're going to say who needs an acknowledgement, who below this number needs an acknowledgement, and we're going to acknowledge back to all the numbers below that the write was successful. And we're going to actually, at that point, that's when we consider the database durable, and we advance to the durability point of the database, saying everything's good up to this point. Another thing that we've done on the Aurora side is we've actually taken and kind of remodeled and re-engineered the thread pooling that exists in MySQL today. So today with MySQL, every connection gets a thread. And as you grow the number of connections on your database and your database becomes more heavily used, that can be a problem. It can lead to performance challenges. It can really burden down your database, having being able to support more and more connections because each one of those wants a thread on its own. Some of that's solved with Enterprise Edition of MySQL, where it's using some thread groups, where it will look and see if it sees anything that's long running. It'll add another thread to accommodate that. But some of the work around that actually involves using stall threshold tuning. And you're using that tuning to actually say, when something's been running so long, add another thread. The problem with that is that you have to really get that tuning done well, because if it's not right, you may end up adding too many threads, which will once again overburden your database, or not add enough threads, which will delay getting things actually processed on the database. So on the Aurora side, what we've done from a thread model perspective is that we've had everything connecting in through ePOL. All the connections happen in there, and behind there is the task queue, which has actually got a bunch of threads that are looking for work when they aren't doing work. They're looking to ePOL for the work that they need to do. And because these are independent, we're actually able to scale up and down the number of threads dynamically based on the number of pending transactions or connections coming in to ePOL. One of the other cool things that's about this is that we can actually, it's aware of when a transaction is awaiting a commit. And while we're waiting for that, we can actually repurpose that thread and let it go and do other work and keep another thread around to actually handle the acknowledgement of the commits when they happen. So it's smart enough to be able to repurpose things so that it gets the most out of what it's already allocated. So with this approach, it's actually, goes back to some of the numbers that Katie showed. Aurora is gracefully able to support well over 5,000 client connections on our largest instance side, which is the R38 extra large. So another area where Aurora has done a lot of work to kind of help improve the I/O traffic pattern is around read replicas. So on the left-hand side, you've got a MySQL configuration with a primary and a read replica. And the thing with read replicas here is that whatever write work the primary database does, the standby database is doing that as well. So in this example, if you've got a MySQL database that is 70% write heavy, only supporting 30% reads, your read replica is going to be 70% write heavy, even though it's supposed to be a read replica. And what that does is it means that if you are expecting to support more reads than 30% with your read replica, you may need to be looking to have a read replica that's bigger than your primary, or you may need to have multiple read replicas in order to be able to support the demand from a read replica standpoint. It also means that you're running independent layers of storage. You've got 2 different pieces of storage that support both your primary and your standard database, which have to be monitored and cared and fed for. And you can actually, depending on the volume of writes, and once again, the latency from an I/O perspective between your primary and standard, they can get out of sync. They can drift apart depending on how much traffic is going through. So on the Aurora side, we've already talked about that the read replicas are tied into the overall storage node, and you can put them into any availability zone. But when you add a read replica, what actually happens is that master database not only ships its redo logs to the storage node, it actually ships those redo logs to all the standby databases or to the read replica databases as well. And what those read replica databases do is they actually look at their cache and say, do I have this or not? And if they don't, they write it to the cache. It allows those read replicas to really, one, have all the data that the master database has very quickly, and two, be able to focus on delivering nearly 100% read-focused operations as a read replica. So let's talk about availability and how important that is. You know, if you guys go through and you architect your applications and everything like that, and you're trying to get everything as performant as possible, it really doesn't matter unless that database is actually up and running. So having the database actually available is very important. So we talked about some of these already. You know, on the storage side, we use a quorum system for both reads and writes, which means that it's very latency tolerant. So if some of the nodes are having a temporary network issue and they can't respond in time, we rely on the other nodes that can respond to us in time. We use that peer-to-peer gossip network to help fill in the holes with the data and any transactions that didn't arrive or any you know, corrupt data that we might find. We use S3 as a backup to help with availability from a data perspective. We continuously scrub the data blocks that we talked about earlier. And then the monitoring. So because it's a managed service, you get all the benefits of the managed service provider actually monitoring those nodes and the disks for repair. The Aurora system and the Aurora team is constantly watching those nodes to make sure that everything is healthy and knowing where they need to go in and make changes or fix things. As Katie pointed out earlier, we store the data in 10 gigabyte segments. And what that allows us to do, it allows us to repair bad pieces of data very quickly because they're not too big a segments, so that we can move them around the storage tier very quickly. And it also allows us, when we identify maybe a hotspot on a disk where a couple of maybe very heavy popular customers have some very key pieces of data and they both land on the same disk, in order to make sure that that disk doesn't become too burdened, we can actually move those pieces of data to other disks. And because they're in these 10 gigabyte segments, we can move them very quickly and frequently. And then the Aurora team, you know, for this storage layer, they've invested a lot of time to make sure that they can add and remove members of the storage node without impacting you. So as new nodes are coming and going from that overall storage layer, you're not impacted by them. There's no freezes that happen because something is coming or going. It still will work and get the appropriate number of responses and just focus on the other nodes that are actually there and available. So things can come and go, failures can happen, they can self-heal, and you won't be impacted from a read and write perspective. So databases, I've seen it, they crash, and they usually don't crash when you want them to. So when a database crashes, you have to first get the database back up. It always happens like 2 in the morning, but you've got to get the database back up. And then at that point, you need to actually checkpoint. You need to find your last good checkpoint. Typically, those are done in about 5-minute increments. And then you're having to replay all the log files from that checkpoint up to the point that the database crashed. From a MySQL perspective, that job is actually single-threaded. So if you're running on a very large box or a very large EC2 instance or compute instance, and it's got multiple cores, it's only going to be using one of them because it's a single-threaded process. On top of that, because there's a crash has occurred, your data is more than likely not in the cache anymore, so it's actually having to go back to disk to get a lot of the information that it needs to complete this process. So there's a lot of extra IOs that happen. And so this process can take a period of time, and it's a little bit unpredictable because it really depends on what's happened since that last checkpoint and what your latency might be from an IO perspective to get all that data off the disk. So on the Aurora side, you know, we've already talked a lot about that all the redo logs are sitting there at the storage layer. So you've got the ability to actually replay all your log files directly from the storage node into your database instances. And what happens is that when you have a recovery, or even if you bring a brand new instance into your cluster from an Aurora standpoint, it's going to reach into the storage layer and it's going to ask, hey, when a query is executed or when somebody asks for data, it's going to reach into the storage layer and say, hey, I'd like this block of data. It's going to pull that 10 gig block of data out. It's going to compare and say, hey, are there any log entries that have actually updated this data block? If it is, it's going to add them in. It's going to return it back to the database node. The thing is that is the same thing that happens if you were just running without a failure. It's no different. And it all happens parallel, distributed, and asynchronous. So it can happen very quickly. So recovery on the Aurora standpoint is almost near instantaneous because you just need to start it up and start using it. You don't need to wait for a checkpoint replay or anything to get caught up to a point in time. You're able to start using the storage and information in the storage immediately. We talked a little bit about survivable caches. We won't talk much more about it, but we have, on the Aurora side, have removed the caching layer from the database. The caching layer operates independent of the database. So when there's a reboot of the database or the database has a failure, your caching layer is going to stay warm. You don't have to worry about spending time to go and replay or to go back to disk to get that caching layer up and running. When you bring your database back up, you're able to fully start running at the level that you were delivering to your applications prior to your failure or your reboot. So when you combine this caching layer, the ability to stay warm at all times, and the ability to kind of instantly recover from your crashes, you really have like this very, very easy path to be able to recover from anything that's a database failure when you're using the Aurora clusters. Okay, so we've got a little bit of timeline here on like kind of how failovers might happen and how they become a little bit more predictable from an Aurora standpoint. So the top timeline is a MySQL database running on RDS. So you have failure detection. The RDS service is going out and continuously monitoring the master node to make sure that it's healthy and that the availability zone is healthy. And when it detects that there's a failure, it's going to start the failover process. And that failover process is going to be moving over to a standby database that you have running for your, hopefully you're running a multi-availability zone and then failing over to that standby database. That recovery period is going to be a little bit variable depending on how much data needs to be replayed from the log files and how much data needs to be caught up from between when the master went down and what the standby has. So that recovery happens, and then there's also a DNS propagation that happens. So when the RDS service fails your master over to a standby database, it actually changes the DNS entries for your database to point to the standby database, which is now going to become your master database. That can take anywhere from 30 to 60 seconds. So at the end of that, you've got your app up and running, but there's a lot of unknowns as far as how long that time might take. So on the Aurora side, you actually have your failure detection that's happening once again. And once that failure is determined, the recovery is almost instantaneous, because once again, we talked about once a new instance comes into play, if it's a read replica, it's already got all the production data, or if a brand new instance has to come into play, it's able to start reading data off of the storage node immediately. So your recovery time is very, very small there. And then your application can actually be up and running right away. So I'm not actually addressing the DNS part here, because one of the cool things here is that we've been working with the MariaDB team, and they've actually created drivers, JDBC and ODBC drivers, that actually work with Aurora. And with those drivers, they're actually aware of all the read replicas in your Aurora cluster. And what Aurora does is that it actually puts an entry into all those read replicas of who the master database currently is. So when a failover happens, the RDS service will actually update all the read replicas to say, here's the IP address of the current master. And the MariaDB driver will actually resolve that and make sure that you're always connecting to the master database. So it allows you to avoid having to worry about any DNS propagation. It allows your application to get up and running a lot faster anytime you have any database instance issues or failures. Okay, and I think this is the last thing for us. So high availability with read replicas. As we all know, the read replicas can be placed in any availability zone. They can be tied into the storage instance. One of the cool things with the read replicas is you can actually define a priority to those. You can say which read replica has priority from a failover perspective. You can also size your read replicas to be a different size than your primary database instance. Maybe your database instance, your primary is very write heavy, and there's not a lot of reads for your read replicas. So maybe your read replicas are sized smaller, or vice versa. Maybe your primary is not very write heavy, and you have a lot of reads coming on. Maybe you size your read replicas higher. What you have the option to is you could have one read replica that's maybe sized exactly like your master database. and set that as priority 0, and that's your primary point for failover. And maybe your other read replicas are sized differently to maybe handle a more appropriate workload. So what happens here is that if there's a failure on your master, the RDS service will promote the highest tier read replica to now be your master database. So in this case, the one that was tier 0 got promoted to be our master database. Okay, all of these things, we've given you the option to be able to simulate those. Katie mentioned earlier that there's real world things that happen out there. Just running tests on empty boxes is maybe not the true statement of how well it performs. So you actually have the option in Aurora to run SQL statements that will help simulate failures. And you can actually use that to see how the Aurora system performs and how your applications perform, whether you're simulating the failure of a database node, simulate the failure of disks, or even simulate some network issues or the failure of a network to see how everything is performing. So I encourage you to go in and test that out as kind of your final validation of how Aurora is working for you and your applications as you're using it. So that comes to the end. We're about to wrap up. I'd like to first of all say thank you to everybody for coming. Make sure you fill out your surveys. We're really interested in your feedback. We want to make this as good as possible. And we'll stick around for Q&A if you want to. Well, if you want to go to the mic, we'll take Q&A. Or if you just want to meet us down here in the corner, if you're too shy, we're happy to take your questions. Thank you. Yeah.
So I noticed there was a lot of eating your own dog food as far as AWS infrastructure, but curiously absent from that list was Kinesis. Was that something that you considered for like the transaction log, and do you feel like it does have a place in the Aurora infrastructure, or do you need something that's a little bit lower latency?
Unfortunately, I mean, the Aurora product was like 3 years in the works.
Yeah.
And Kinesis is a little bit, it's been a couple years out, and although I wasn't part of the team for that, I'm sure that they had to rethink it. Maybe Kinesis would play into it, but I'd also say that Kinesis wasn't there when some of the key components were built. But I would have to go back to the team more specifically and say, is Kinesis a good fit or not, to answer that question entirely.
Cool. All right. Thank you.
Yep.
So what are some of the challenges you guys faced supporting Expedia to use Aurora?
Do you have anything to say on that?
Did Expedia come to you, try to resolve some of the issues with Aurora?
All right. So the Expedia, as I mentioned earlier, their issues were related to cost and performance scaling. And they explored other things on Amazon like Cassandra, Solar Index, but they eventually zeroed down on Aurora for its superior cost performance as well, cost characteristics as well as the performance they were able to drive out of it. So, is that your question, or?
My question was there any challenges above that you guys got to solve?
Okay.
So that is not in the public domain right now. So can't really share customer details unless they want us to.
Are you interested in talking to them as far as what they did, or are you looking for? Okay. Okay.
Because it's only after last year, right?
Mm-hmm.
So Aurora was announced in November 2014, and then it was in private beta for a few months, and general availability was in July. I'm not sure when Expedia started their journey with Aurora, maybe as beta or after it was GA, but yeah. Aurora has been around for some time. It's just July last year that we made it widely available.
I can tell you, I mean, we're very open to customer feedback. We live and die by customer feedback. So a company like Expedia, if they were using Aurora, I'm sure that there was some feedback that was given to us. We're pretty agile to be able to roll changes into the environment, do patching for the Aurora database. So I wouldn't be surprised if there was some feedback, but we don't have the visibility on that.